the B Research Gamma Spectrometer. Finally, gamma spectroscopy for the people! Or at least not so freaking expensive. Yay! Okay, so this is the Gamma Spectacular from B Research, an Australian company down under. And they make this little guy right here, which allows you to get into the wonderful world of gamma spectroscopy and nuclear physics for pennies on the dollar, quite frankly, compared to other devices. And that's not to knock other devices. I have several gamma spectrometers, and I like all of them. They're all really, really, really nice, and each one has different features. So this one's real claim to fame is that it's massively less expensive than other units, while offering you still a really, really versatile and very, very portable unit, because I can't carry some of my larger stuff around with me, but I can carry this. Not only if I broke this is a lot cheaper to fix or replace, but it's also small. Look how tiny this little thing is. It doesn't weigh anything. This little unit right here weighs maybe, what is that? Weighs maybe half a pound, and a pound is, let's see, 2.2 pounds is a kilogram, so it's like a fourth of a kilogram, I guess. I'm trying to get that off of my head. Remember, I'm in the United States, so we really don't use metric too much unless we're doing science things. But anyhow, here's the device. Basically, it has 3 cables that connect into it. This is a USB connection. Let's plug it in. This provides power from the laptop or the desktop computer. That's all this provides, just power. That's it. Simple as that. And it can be powered off of this laptop, which is not currently plugged into anything. The cable you see going in is actually going to the camera you're looking at. So I might run out of power and have to plug it in after a little bit, but you can take this in the laptop out in the middle of the field somewhere and actually do an analysis right on the spot with this. You don't have to have any high voltage source. This is a high voltage source. So power goes in here, and it gets converted. Your voltage goes up and your amperage goes down. And that gets converted into 600, 650, 700 volts, 750, 800, 850, 900, 950, 10, 1050, and all the way up to 1100 volts positive. Yes, that's a lot. And that's enough to run most common detectors. Now, yeah, you can get detectors that require a lot more voltage than this, but your average detector, most of the ones that the average person is going to be able to afford and use, are going to be within this range. So that's quite useful. Now, that gives you your power. So let's show you how you connect your detector. We take a connector like this. This is a BNC connector. See? It turns in, twists like that. This is a BNC connector, and it's going to connect to your detector. Like that. Done. No rocket science. Easy pie. So there you go. So now we have voltage. I'm not going to plug this into the laptop quite yet. You have voltage going to the actual unit, which has been converted into higher voltage for the detector. So how does the signal go back to the computer if this is only handling voltage? Well, this turns the energy that comes out of this, the signal that comes out of this, converts it into sound. So you have one of these, 2.5 millimeter detector like you'd get on headphones. You plug this in here, plug this into the input jack in your computer, your microphone input jack, and then you're good to go. Here's what happens. When a radioactive source, when something radioactive, like this piece of cesium-137, the cesium-137 sample right here, when it hits the crystal inside of here, the gamma rays hitting the crystal will produce flashes of light. The intensity, the number of photons produced, is proportionate to the amount of energy of the gamma ray that hit it. High energy gamma ray, lots and lots of photons. Low energy gamma ray, a couple of photons. Those photons then hit a little photocathode. And that photocathode in some ways is sort of like a solar panel. It's obviously not a solar panel, but the concept's very similar, the photoelectric effect. The photons will hit that, and they will produce electrons as a result. They will discharge electrons as a result of impacting the photocathode. There's something called a photomultiplier tube that's inside of this. Those electrons that are very few, just a few that are released, will be pulled down a chain of ever increasingly powerful dinodes. And dinodes attract the electrons, and as the electrons move down the dynode path, they get more and more electrons flowing with them. They build up, being more and more energized, and eventually they hit the very, very end here and are sent down as a signal. The proportionality remains all the way through. High energy gamma, lots of photons, more electrons, becomes a stronger pulse. Low energy gamma, not so many photons, only a couple electrons, still builds up, but the resulting pulse is less. Proportionate. The resulting sound output is proportionate too. High energy gamma, big volume. Low energy gamma, little volume. And that is the basics of how the unit is capable of determining energy. Now, of course, that's different from a Geiger counter, which does not do that. The Geiger counter produces a single pulse of current when it detects something radioactive, which is always going to end up in the same thing, which is one click. Low energy pulse, click. High energy pulse, click. No matter what, nothing but a click. Which, by the way, is not to say anything bad about Geiger counters. I wouldn't go around without one. As you can see, I have two of them sitting right here. Why? I like them in the video. They look nice. Anyhow, so we have our unit here, and we're going to hook it up. Now, some things you need to know, some common sense stuff. First and foremost, I'm not going to be using this detector because of the type of detector it is, and I'll go into that in just a minute. But first, let me talk about cables. Detectors have usually two types of cable connectors in the end of them, and this is, by the way, the quick explanation. There's a lot more information you could get into, and I'll put a link in the details section about a book that I would recommend getting if you're interested in this. You're going to end up getting a single connector that has signal and power together, or you're going to end up with a dual connector which has signal and power separate. These types are usually lab grade units, which isn't to say that any unit like this isn't, but typically these are more like lab grade units. They separate the two because it's less noise. The two don't affect one another as badly. But when you buy one like this, you're going to need something like this. Two goes in, one comes out. So basically put, it's a connector that integrates them, a splitter if you like, or a, what would it be, a uniplexer? But anyhow, this one has high voltage signal, goes to high voltage and signal going out. This one's a geoelectronics one. You can also get it from Spectrum Techniques. I'll put the link in my details section. Spectrum Techniques, by the way, great place to get these sorts of things. Geoelectronics, another good place. All right, so that allows you to deal with both of these two types of connectors. Or sorry, yeah, the connectors in the end. The other thing to know about is the actual connectors themselves. Let me see if I can get you an example. Here we go. The two types of cables you'll deal with: BNC cables, miniature high voltage cables. They are nearly the same, but they're not quite. They go on and they twist, same sort of way, but the difference is this one has a slightly larger piece, the little white piece in the middle here. It's extended a little farther than this piece is, and they don't quite fit onto one another. This is designed for higher voltage than this is, although quite frankly they're nearly interchangeable. You can go on websites and buy brand new ones for $60, $70 a piece, but I'd recommend going to eBay. You can buy a good one for like $8 to $10. The B Research unit uses a BNC connector. I bought this one at a store for I think $10, $15. This cable. If you're going to get really hardcore into this, you want to probably spend the time and pick out a really good quality cable that has really good shielding and so on. But technically speaking, any BNC cable would work. The miniature high voltage connector will not connect to it. It looks like it'll connect, but it will not actually connect. And what you can do is buy something like this guy that I have right here, which is actually a miniature high voltage on one end, BNC on the other, because some probes, like this probe, is miniature high voltage. So it's sort of annoying. It's kind of like two cables that really should connect but don't, and there are some reasons why they don't. But so pretty much this is just boiling down to cables. Which one do you have? Read your manual when you buy your probe and your device and make sure they hook up. If they don't hook up, make sure you just buy a converter. Very simple. All right, so now you have everything you need. So let's talk quickly about detectors. First off, detectors like these guys are crystal detectors. You are not going to be using a semiconductor detector with something like this, like a high purity germanium detector. Besides, if you spend the $10,000 to $20,000 for one of those, you probably already have all the rest of your equipment anyway. These detectors are crystal detectors. They have a crystal inside of them. The crystal is excited by gamma rays, which does that whole effect I explained a few minutes ago with photomultiplier tube built into them. There are many types of detectors, from micron plastic scintillation detectors. These are scintillators, by the way, BGOs, and so on. But two of the most common ones used for gamma spectroscopy are going to be cesium iodide, CSITL, if you've ever seen it before, and sodium iodide, NaITL. And the cesium iodide typically seems to be a little bit more rugged, but the sodium iodide produces a better quality spectrum, typically speaking. If you're going to run around outside, jump out of windows, and do Indiana Jones sort of stuff, like, you're out in the desert, walking for days with your equipment, and searching for uranium, and you've got camping supplies, and you're wrestling, bears and stuff, I would suggest this type. Or not this very brand per se. Not there's anything wrong with this brand, but I mean not necessarily this exact probe, but I mean a cesium iodide thallium doped probe. If you're going to be in a lab and you're not going to smash stuff up too badly, I'd recommend the sodium iodide. Sodium iodide is going to give you a better picture. You're going to get a better spectrum in general. There are many places to buy your probes from, and I'll put in the details a list of several places to get a probe, and you'll want to contact the manufacturer first. And you can always contact B Research, and they'll tell you if the probe's compatible. Like Ludlum makes probes that are pretty good. Spectrum Techniques has really good probes too. They have really good probes. But B Research also sells a probe too. And if you're on a tight dollar and you're trying to get a setup and you don't really want to spend thousands of bucks, you might go to B Research and just buy their probe. They have a probe, a sodium iodide probe and unit. And I think the combo, I think it's like $700 or $800. That's not bad. That's a good price. Now this unit right here, this can cost you $1,200. Nice probe. This, $400-$500. Depends. Whenever you can, I would always go for the sodium iodide probe over the cesium. I really would. I would recommend that big time. Now, the next thing to know is the size of the crystal, because with gamma spectroscopy, size does matter. The sodium iodide probe here is a 1.5 inch. The crystal's 1.5 inches thick. Now think about a bunch of trees, and think about somebody shooting a gun. The gun is the radioactive material, the bullets flying out of the gamma rays, okay? So if you have a bunch of trees and the trees represent the crystal, if the trees are really thin, just a few trees, it's very likely the bullets will go right through and not hit a tree, right? But if there's lots of thick trees, then it's more likely the bullets will stop when they're hitting the trees. They won't make it all the way through. Same works with the crystal. This is a thin crystal probe, and that's not indicative of cesium iodide probes. That's indicative of this specific model. You can get a big fat cesium iodide crystal. You can get a big one, no problem. And if you did, that would be great. But this particular specific unit is a low energy gamma probe. It's a little tiny thin crystal. It's like a few millimeters thick. That's wonderful for low energy X-rays. But it is terrible for broad ranges that you'd want to look at normally. So this is a beautiful probe for things like XRF, and if you don't know what XRF is, you probably don't want to get into it anyway. I can explain if you're interested. This guy, however, has a 1.5 inch crystal. Big thick crystal. You can get a 2 inch too. And these big thick crystals, they capture a lot more of the photons. You get a broader range. Now let me explain ranges. Most people that are going to be doing amateur gamma spectroscopy are going to be looking at photons that come in that have anywhere from perhaps 10 to 15,000 electron volts of energy. And we'll say 1,000 electron volts of energy is a kilo electron volt. So they're going to be anywhere from, let's say, 10 to 15 kilo electron volts to as high as perhaps 1,500, maybe even as high as 3,000 kilo electron volts. All right? And anywhere from, let's say, 10 to 15 kilo electron volts up to perhaps 3,000 kiloelectron volts is going to capture nearly all the photons you're ever going to want to care about. For most things, like uranium is going to be down there below 700 kiloelectron volts. And cesium-137 is going to be right at 662 kiloelectron volts. You know what I mean? Potassium is going to be at 1,461 kiloelectron volts. So they're going to fall at different levels, and those different positions that they fall in, those energies, are how you're going to, those are the fingerprints that you're going to use to detect them and identify them anyway. But you need a probe that's wide enough to see all of it, because if you can only see a little narrow part like this guy, then that makes this a really specialized tool that's only good for certain things. And that's not to knock it. This is a really cool probe, really cool probe. But I would recommend something like the sodium iodide guy right here. You can buy the B Research one. Spectrum Techniques has one. Ludlum. The B Research one looks like it's probably the best deal right this moment. And these guys right here have a big wide crystal that's able to pick up a nice large energy range, a nice broad one. To put it in contrast, this guy right here can see as little as 8 kiloelectron volts, which is very low. But after about 500 kiloelectron volts, it just drops to almost nothing. Its ability to detect, meaning if 100 gamma rays at 500 electron volts hit it, it might only pick up like 5 of them, 3 of them maybe. Whereas if 100 of them hit it at 10 kiloelectron volts, it would probably pick up like 80 or 90 of them. This guy right here has a range of about 12 kiloelectron volts to approximately 3,500, maybe even a little bit more. Not bad. Same with that guy right there. My Polymaster is 40 kiloelectron volts to 3.5 million electron volts. Not bad. But anyway, that's your basics on your crystals, your kind of crystal 101. So we're going to get rid of this guy. And by the way, for SE International that makes this, I love you guys. Nothing wrong with this probe. It's just that this one's specialized for low energy. They actually make an RAP probe that's like this, that's specialized for larger, broader ranges. I think it's like, what is it, a 640 or something like that? That unit would actually be pretty good as well. So let's put that away. Now let's hook up the probes and let's get detecting stuff. And then I'll explain what all this stuff is for and what to do with it. Okay, let's connect everything up. First off, let's connect the unit here. We're going to take the audio cable, plug it into the Gamma Spectacular. We're going to plug the USB cable into the Gamma Spectacular. Make sure the power is set to off. If you have everything connected to it, then that's fine, but you really don't want to have this not connected to anything with the power already on. It's not good for the unit. And in fact, you should always have this off before you plug it in anyway. Never plug in electronics when they're set to the on position. It's just not very good for them. Now we're going to plug in the USB cable. If I can do that right. There we go. And you'll get this bright blue light that'll tell you that it's good to go. Next, we'll take the audio cable. When I plug this in my laptop, the laptop will detect that there's new microphone input because it thinks of this as a microphone, because that's sort of what it is. It's listening for gamma rays, if you like. And I'll show you how to adjust that in a minute, but I'm not going to use the camera for that. I'm going to actually use a on-screen recorder when I do that, because honestly put, as we all can imagine, the camera's not the best way to look at what goes on the screen. So I'm going to show you the hardware part of it first. Then we'll get into how to use that next. Now, if this detector were the B Research detector that has a BNC cable in the back, or if this just had a BNC cable in the back, I could just hook this right to here and hook it right to there, and we'd be good to go. But this unit, unfortunately, has 2 connectors coming out of the back of it, so we need to use this little splitter box. It's actually a combining box, not really a splitter. I guess it depends on which direction you're looking at. But so we're going to plug this to here. And remember, if you have power on, you can get a nasty little zap out of these things. I mean, that is 1100 volts. I know the amperage is really low, but still, just don't lick your fingers and touch it. Probably not a good idea. So let's see here. Let's plug that up. Now we have signal and high voltage coming down this cable. I would recommend, by the way, using shorter cables than I have. Always use the shortest cable you can get away with, because the longer the cable, the more interference. Also, look, they get all tangly. So short cables are good. Now let's hook everything up to the detector. And in fact, for safety purposes, I'm going to unplug the B Research device, because it might just be the best idea not to have it plugged in at all when you're hooking stuff up. Signal is BNC. Signal on here, nicely named on the unit. And then last but not least, high voltage. High voltage. High voltage. So I got these cables here, and I'll put them all out of the way in a minute. Let's do something about this cable, because this cable is kind of like in the way. I know what to do. I know exactly what to do. I'll take this extra detector that I have sitting here, and I'll hook it up to my CDV 700. There we go. That works out nicely. Let's cut the volume down. There we go. That's what we can do with this detector so that it gets out of the way while we're using it. All right, so we've got all these cables hooked up. We can now plug the power up to this. And we are good to go. If we were to cut this on right now to the correct power, we could then start working with the software. Now, before we do that, let's understand how to make a testing environment. So let me just kind of move all of this out of the way and we'll set up a testing environment. We might have to unplug a few wires to do that. All right, so we're going to work with some lead, and the reason that you want to do this is because there's radiation all around us all of the time. This probe that we're going to use, it gets 3,600 counts per minute background. I mean, as you can see when I connected this scintillation probe up here, how much, let's flick this to ×1 setting, how much higher the background was in this. This thing has a background of, what, 150 to maybe 200 counts per minute? Scintillation probes are much more sensitive than their Geiger counter equivalents. And so to do this, we need to make sure we block a lot of the background. And lead is a good way to block background. Now, when working with lead, wear rubber gloves. Because quite frankly, the lead, and I'm not a medical doctor, so I'm not going to make a claim as to which one is more dangerous, but I do know for a fact that the lead is extremely troublesome and can be dangerous if it gets inside of you. That's not to say that touching lead you're just going to drop dead or anything like that, but I mean, it's not good to get it inside of you. In the same way, it's not good to get radioactive things inside of you too. You should use precautions against both. Now, I need to go buy some more latex gloves. These are these crappy vinyl gloves. I recommend not buying vinyl gloves. Why? Because vinyl gloves are terrible. They are horrible. Unless you have an allergy to latex, and even if you did, well, I shouldn't say that. If you have an allergy to latex, I guess you're stuck with vinyl. But other than that, I would buy latex in a heartbeat. So you're going to see in just a second why vinyl is so terrible. Like, first off, they're all like pre-sized and such. Oh, that's horrible. Buy latex. Never buy vinyl. I didn't realize when I was in the store. I didn't realize. This is all my fault. This is all my fault. But anyway, considering that a box of latex gloves is like $4, and they come with lots and lots of latex gloves, and considering that lead can be harmful, and even if you wash your hands, it's not always going to get it all off, and if you have like little kids around and stuff, it's just a smart idea. Now, these bricks haven't been painted in a while. They need to be repainted. You can see moving around bangs them up. But when you get your lead bricks, I always paint them with something like this has a kind of a gold metal paint put over it. It's a metal paint that's designed to paint like chairs and stuff outside to make sure that the rain doesn't get to them. This will prevent a lot of lead from getting spread around your house, because you really don't want to get it spread in your house. This block right here looks to you like it's just a block of lead. I got it off of eBay for like $1.50 a piece, but I sprayed it with a clear coat. But there's still going to be lead on my fingers because it's starting to come out a little bit. You want to repaint it every 6 months or so. You might want to make sure that you test your paint can before you use it to make sure the paint can doesn't contain anything radioactive in it, like some kind of potassium, or else that can mess up your results. Anyhow, $1 or $2 a piece off of eBay, you can buy these, bulk shipped to you. RotoMetals.com. All of this is in the details section. Please look at the details section. It's all there. All these links to these addresses are there. Roto Metals sells these for approximately, what is it? I think it's $2 a pound. And this is 5 pounds. And a kilogram is 2.2 pounds. So I think it means that this is like 2.2 kilograms. I think that's how the conversion works. It's still kind of loud. There. So basically, this is a couple kilograms of weight, and it's going to cost you about $10 a piece. I would suggest buying a minimum of them. Get your detector, or if you can't wait, if you want to buy it all at the same time, measure your detector out, and so on, and then buy what you need for it. You can also buy something like this from Spectrum Techniques. They sell the lead donut. The lead donut's great because this fits directly inside of this. So, oh wow, that makes my skin look really, really weird. Okay, so here's some lead options for you. You'll need that for your detector housing. I actually have 20 or 30 more of these, and I have a huge thing built up. So I have a large enclosed area that I can put stuff in and fully seal it, which is how I get my good samples. But just a few of these will make a world of difference. You want a thermometer like this, a digital one, a sensitive one. The reason is that temperature affects these probes. When the temperature drops, the place where the spectrum energy is found for a particular energy will move and tend to shift in the screen. And if the temperature is going up and down inside of your house during the time that you're running a test, it can kind of take a nice thin peak like this, nice beautiful peak, and it can kind of shift it back and forth and kind of smooth it out. And it will drift away into nothingness. It's kind of like if you had a sand sculpture and you just shook the sand in the box, it would just kind of blur it away until it was nothing. So this is useful for making sure everything's right. We're at currently 23.9 degrees Celsius on the end of this, and 24 for this because this has dual thermometers. These are useful too because you can put one on top of your detector and one inside and get a good idea of how things are going. And if you see the temperature shifting on the top, the outside part, this is the benefit of having the dual one. Then you can go over and like open a window or something and take care of it quickly before it starts to affect the bottom. See, the bottom one just went up to the same price, or not price, temperature. Price. That's funny. So if I hold on to it, it'll probably go up because I think that's colder than my body temperature. I don't know. I'm terrible at Celsius. Oh wow, that went up to 29. Okay, so obviously my body's warm. Okay, so you'll want some lead and a thermometer. You will need something radioactive for calibration. If you're afraid to have something radioactive, then maybe gamma spectroscopy is not for you. You can do some simple stuff. For example, a can of light salt, potassium chloride salt from the store, that can be useful because you need 2 fixed points in a graph. Remember, if you had a graph and I showed you a graph and I said, okay, well, here are my financial earnings for the year. If I don't have the sides labeled, if you know that money and time, but you don't have any other labels, then you don't know. Is from change from here to here, is that change from $5 to $10 or 10 million, 5 million to 10 million? You don't know. You have to, if you've ever worked with graphs, you know you need to have at least 2 fixed points. And you would need to know that at this point, it was 1 month and $5, and at this point, it was 10 months and $1 million, and then you can calculate between the two of them, right? For calibration. And so you'll need 2 fixed points. I recommend cesium-137. Here's 2 samples of it. Cesium-137 produces 2 beautiful energy lines, one at 32 kiloelectron volts and one at 661.66, right across the board. 2 absolute perfect. It's almost like nature made us the perfect calibration source. The difference between these two is that this guy right here is 80% accurate on the amount of that's in it. Plus or minus 20%, this is about 37 kilobecquerels. This guy has been assayed to 95% accuracy, so plus or minus 5%. This has 3,737 kilobecquerels. I just happen to have that memorized. For most people, this guy is good. You need assayed amounts like this if you're going to do an analysis of how much of something is in something, and you want to be really precise, because you can be precise with this, but you'd be really, really, really precise with this. The difference in cost from Spectrum Techniques, $50, plus or minus. I'm not telling you their price list. I mean, it was about how much I paid. It might have gone up a little bit, but it's around 50-ish. This, $150. So add $100 onto it. If you have a piece of rock that contains uranium, and you have a container full of potassium chloride light salt, well, this doesn't have anything in it, but pretend it did, then you would have 2 fixed calibration points as well. So you can do it a bunch of different ways. But there's really very little harm in owning something like this. I mean, don't duct tape it to your body. Don't swallow it. Don't sleep with it under your pillow. Just take it, put it inside a lead container like this, and don't put it in the room where everybody is. Don't expose yourself to it all of the time, and you'll be perfectly fine. All right, so there you go. let's move these aside, and let's build ourselves a lead castle. Now, scientists call them lead castles. They're the enclosure that encapsulates the probe. Now, my hands could have lead dust on them because I touched lead. I don't see any lead dust. I always clean all my equipment off, so that's perfectly fine. But keep that in mind if you're going to reach over and handle a probe after you touch the lead, that you could be cross-contaminating that. I always clean my stuff off, and I don't mention this in my videos, and somebody recently brought it up, and it occurred to me that I don't really tell people that. I just kind of assumed that they knew, I guess. So I guess I should point that out. I like to clean my stuff afterwards. You could even go so far as you want, if you want to, is to actually put something over this to protect it. It's going to sound kind of odd, but a condom actually works pretty well. That'll keep the water off and everything. All right, so move these out of the way, and I'll show you what this is in a minute. This is a bag of soil, a soil sample. And I'll show you what this is in a minute too. All right, so let's make our lead castle. Be sure never to put this here and then put lead around it, because what if you drop the piece of lead? These things are freaking heavy. They'll destroy your probe. Now, if you want ideas on how to do it, ask a 5-year-old. Don't let them touch it. It's lead. But trust me, kids probably would give you the best ideas. Give your kids some wooden blocks, because wood is safe, and let them show you what they think the best shape should be. And then duplicate it. But like I said, don't let them touch the lead. That would be bad for them. Here we go. That's that. Which direction are we going to put this in? I'm going to have to move these lead bricks out of the way. This is already putting dust on my plastic here, so I'll have to clean that off too. Put that in there. And like I said, this is kind of a simple testing chamber because the source is going to be sitting on the outside and exposed. A really good one would fully enclose it. And what I'd recommend you do in that case is you just get your measurements down and draw it out. Okay, I want to have 2 inches for the detector and another inch on top, and I want all these inches over. And then you contact someplace like Roto Metals and ask them, how big is this thing? This is, let's see, what is that in? That's in centimeters, just 21 centimeters by, looks like 2.5 centimeters by, looks like 4 centimeters. Yeah, I did that kind of fast, but you get the idea. And inside of this is the detector. Move that over a little bit. There we go. Now, you might have been asking, what's this for? Well, things like cesium here produce gamma rays, but they also produce beta rays, and also there's things like beta particles. And there's also things like alpha particles. These particles aren't directly detected by the detector, but what happens is when they hit the metal in the detector, they slow down rapidly, and all that energy of slowing down has got to go somewhere, right? Energy is not destroyed. It's never created or destroyed. It's just changed. And so that energy gets converted into X-rays. You get all these little X-rays all over the place, drive you absolutely nuts. Using something like aluminum here slows them down more gradually, so they're not as big of a trouble. I like to suggest putting aluminum in front of my detector if I can avoid it. It's a good idea. Good idea. All right. And now we can take this cesium sample, put it right up in the front, and use that to calibrate our unit. That's pretty simple, right? Let's move this lead out of the way. And we're going to test this sample. This is a sample of soil from right beside the uranium mines in Virginia. Now, this sample is actually not particularly hot, unfortunately, but we'll see if we can detect any uranium in the sample. All right? And here's a piece of the rocks that are from that area. Look at those neat rocks. Aren't they just neat? Okay. So let's hook this up and get these gloves off and get to some testing. All right, so here we are, and we're looking at the audio input. And this is on my laptop, so let me get rid of this. Let me show you the more official way that you're going to find it on your laptop, because you don't want to be confined to just whatever my particular software is. And I would point out that laptops are not going to probably have as good a sound cards as desktop computers, and I would recommend a desktop computer to do this, but a laptop's perfectly fine too. It depends all on the quality of output you're looking for. All right, let's see here. We're going to go to my sound settings, and we're going to go to Mixer, and I'm on Windows 7, by the way. This is going to be a little different on XP, or I'm not actually sure how you set it up on a Mac, but somebody else I'm sure can show us how to do that. I'm going to go to my sound settings. By the way, I could get here through the control panel. If I go to control panel sounds, let's see, control panel, and where is sounds? Sounds. Windows 7, the way they do it, I always have loads of trouble finding anything in Windows 7. All right, so adjust volumes and sounds. Well, that just goes there. Manage audio devices. Aha, here we go. This is the same way I was doing it before. Okay, so anyway, either way gets you here. And you go to recording, and you have multiple inputs. Like here's the one I'm speaking on. See, test. See how that went up right there? That's the one I'm talking on. And this guy right here is the one that comes from my detector. And we want to go to properties. Boing, boing. Now, here is the volume coming in, and this is kind of like a booster that it has. So the question is, what setting to put this on? Now, I happen to already know, because I've tested it, that 10 is the best setting for me, for this detector. No, I'm sorry, maximum is the best setting for this detector. But how do I figure that out? Well, I'll show you. The first thing to do is you download the software Intune, and you download PRA. These are the two pieces of software, and there's links to this. You can get them several places, but I got them from the B Research site. They're both completely free. They install on the computer very easily, and you run them. Yeah, sure, I want to run it. Don't ask me questions. All right, there we go. We'll expand that to full. Now we're going to change the voltage on the unit, and I'm going to set it to 850 volts, which is within the operating limits of my detector. I would warn you very much about to be very careful about the actual voltage that you supply to your detector. You need to read your manual. If your detector only goes to 850 volts, don't go over 850 volts. Typically, the detector can take the additional voltage, but to do so is going to greatly reduce the length of its life. And do you really want to buy a new detector soon? I know I don't. So you be really careful with your detector. All right, so I have the little dial set to 850 volts, and I'm going to click this button right here to record, and it says where do you want to save it. I'm just going to save it to the desktop. It doesn't really matter what file I save this to because I'm not going to use this file. And here's my sound. See it going through? That's actually coming from the cesium-137 source. And I'm going to sample a couple seconds. And what I'm trying to do is figure out if my sound is too weak or too strong or what's wrong with it, if it's right. And I guess the longer you did this, probably the better. What I'm trying to look for is the sound to be in the right spot. So let's stop this, and I'll show you kind of what I mean by that. Let's expand this now to full screen. I said, oops, expand to full screen. Expand to full screen. There we go. Well, it's not really wanting to expand to full screen for some odd reason, but anyway, let's look down the middle here. As we pick these lines of sound and we go along through them, you'll notice that their arbitrary units right here show the actual magnitude of the sound. Like this guy goes all the way to the top, and I bet you this line right here goes to the top too, right there. Yep, all the way to the top. But the majority of them seem to be around maybe 30 to 40. And what we're looking for is probably around 50 to 60. So if this were really low, like if these peaks were really low, let me see if I can simulate that for you, what really low looks like. Change this level. Let's jack this down to 7. Okay. Let's do it again. Give you an idea. See how much lower those look now? The volume's too low probably. And we'll stop this. And as you can see, the arbitrary units you're looking at right now are between -1 and 5. So the maximum you're looking at here is 5 and 6. That's no good. You hit some of these high peaks right here that hit 30, still no good. This is too low. And what you'd want to do is keep increasing the sound until you got it to where it was around 50 to 60. I'll go up to, let's say, 100. I like 100. And record again. So hopefully you get the idea what I'm doing here. I'm jacking the sound up until it's right. And the reason is the sound pulses that come back are going to come back at a particular kind of arbitrary fixed amount. There's a minimum and a maximum to them. And what you're doing with the sound volume device here is you're increasing or decreasing that value in order to boost the signal to make it work out nicely in your software. And in fact, if you want to, you can actually play with the sound until you get it right, and you can make a much better spectrum spectra if you spend the time to work on getting your sound right. I'm not going to go into too much detail about what settings to put it to, because they're really going to depend on your detector. For example, that little thin crystal one I use a volume setting of 10. For my bigger crystal, I use a volume setting of 90 to 100. And as you can see, now we've come back to where we were before. The units on average look like they're around anywhere from 50 to 80. The high ones go to 100, which isn't good. They all hit all the way up to 100, but it's not too bad. So we think we're probably good on sound. Now, next up, we want to start PRA. There's PRA. PRA is running. This is PRA version 8, by the way. First thing on the agenda, once you have everything set up, is to go down here to Data Acquisition and Analysis under Settings. And there's some settings you want to modify right here until you get them right. Now, basically these settings have a lot to do with the pulse shape. Because if you remember when the pulse shape came through, it looked kind of like a heart monitor when they look at somebody's heart. And the pulses will come through slightly different shapes, and what you're going to try to do is tell the computer, how true do you want to be? Do you want to be absolutely only accepting pulses that are perfectly shaped right? Or do you want to be really lax and allow any old looking pulse to be measured? Because you're going to get background interference and all kinds of deformed looking pulses that come in. And pretty much I have this set the way I'm going to use it right now, 0.5 to 0.7 right here. You're going to want to play with this until you get it right. The actual manual explains more detail about this. But basically when the numbers are set really low, like 0, they have to be exactly the pulse shape to be counted. So if hundreds of pulses go in, I'm only going to probably detect 1 or 2 of them that are perfectly right. So very few detections will be right. And the benefit to that is, of course, you're probably only going to get valid pulses. But the downside to that is you're going to lose lots of probably valid pulses that aren't perfectly exactly to shape. So it's how much you want to how accurate you want to be. If you set that to 1, then it'll take any old thing. So a value of 0.5 seems to be pretty good for me, and you're going to want to play with your detector until you get it right. And by the way, you're going to want to have the shape tolerance method selected. Now, these settings can be played with from low to high without hurting or damaging any of your equipment. You can change them all day long until you get it the way you want it to be. We're going to ignore the rest of this stuff right down here for now, because a lot of this is more complicated stuff not needed for the basic operation of the unit, because I'm sort of just kind of showing you how the unit works. I'm not going into the extreme detail of configuration. Bin size and arbitrary units. This number here will affect how many little channels you have going across the bottom. It's almost a scaling number. If you set it too high or too low, you might find that you have too many or too few channels. I have it set to 0.1, and I'll show you in a minute what happens when I change it to a higher or lower number. That might make a little bit more sense to you. Use energy calibration checkbox should be unchecked to start with because you haven't calibrated yet. Once you calibrate the unit, then you'll want to check this box to fix that. And I'll show you what these other units do in just a minute. I'm just kind of giving you the most basic thing you'll need to start with. We're going to save this. And now what we're going to do is we're going to start pulse shape acquisition. Now we're going to capture pulses, a couple thousand pulses. And the reason we're doing this is we're trying to get the unit to learn what our pulse shape should look like. And it's analyzing all these pulse shapes coming in, and it's trying to figure out which one is the right shape. Everything you see going on right here is actually happening in the PRA software, not the actual Gamma Spectacular. And there are several other pieces of software you could use instead of the actual PRA software. So you're not actually stuck with PRA. You could use the Thermino software, and there are some other ones. I tend to like PRA because I find it really quick and easy. PRA is very simple to get basically up and operational, but it can become kind of complicated if you want to get really, really deep into it. But in some ways, it's more simple than a lot of my other software. All right, so we've calculated 50,000 pulses. If we were doing a background, we might only get 1,000 pulses. So 1,000 is probably perfectly good. Maybe 30 seconds to a minute worth is fine. So we're going to stop data acquisition. And this box will pop up, pulse shape. These values indicate the pulse shape. And you might be immediately thrown back saying, whoa, 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 look at all these crazy values. How am I supposed to know that? Well, you don't. This is showing you what the machine has set it to. For the starting beginner user, you can click OK and just let the unit go with what it decides. It'll probably be OK. Now, let me show you what a cesium-137 spectrum should look like. Here's what it should look like. All right, so we're going to want our spectrum to look like that, somewhat like that, okay? And that's one reason for using something like cesium-137 that's well known, so you don't spend all day long trying to chase down random peaks all over the place trying to figure out what's what, because it can get kind of complicated if you don't have the calibration down to start with. We're going to go to Action, and we're going to do Start Data Acquisition. We're now acquiring a spectrum. We're going to go to View. We're going to go down to Pulse Height Histogram. This is the actual spectrum forming. And let me go up here and stop this. Stop it. We're going to start it again. And I want you to see what it looks like from the beginning when you first start. That'll look kind of neat. So let's kind of expand this out. And let's start it again. Start. And you notice PRA automatically adjusts this back and forth, right to left, based on the number of the energy pulses it finds. Like it's finding some higher energy pulses over here. There's other stuff that's out there and that's exciting the detector. And so it's expanding itself. If it hadn't found anything but to maybe right here, then this would be expanded only all the way across. So it's auto-scaling. Now we're in a linear mode right this moment too. And we'll switch to logarithmic view in a minute. And that's how it describes this. Basically, you have counts going up and down. This is the y-axis, and it's counts. This is the x-axis, and it will be energy from low energy over here on this side to high energy over on this side. Now, I already know what these energies are because I'm just kind of familiar at looking at these. This peak right here is 32 kiloelectron volts. This peak right here is the primary photo peak for cesium-137. Technically speaking, barium-137M if you want to get into it, but whatever, cesium-137, and it's at 661.66 kiloelectron volts. There you go. Cesium-137 right on the dot. This is the Compton edge, and that's the backscatter peak, and that's from the lead shielding right there. So these are sort of common things, and you might be saying to yourself, wait, hold on, what? How do you know that? Well, you learn that over time of doing gamma spectroscopy, and I will go into a more detailed video that explains how to determine, like, is this an actual peak, and what is this, and what isotopes are we looking at here. I'll go into a detailed video about that at some point, but for right now, I'm going to just show you this. And when I do go into that video, by the way, for isotope identification, I'm going to use this software because lots of people will use this kind of software as opposed to my more expensive software. So let's calibrate this unit. First off, these settings here look like they're probably right. I should probably show you what happens if we change them. So let's change them. Let's make it 0.1. I don't have any right channel. I only have left channel. So I'm like, I'll change both just so that nobody gets confused. All right. We're going to stop the acquisition. We're going to apply this new setting of 0.1. Did I click apply? Yeah, I'll click it a couple times. And we're going to do a start pulse acquisition. And I ignore this pulse height histogram when I'm doing that because it looks all crazy looking. Get a few thousand pulses. Stop it. Accept the new values, and then we're going to run the whole thing. See, now it looks a little better. This is what it looks like when I change it to 0.1. Less pulses are being accepted. A lot less pulses are being accepted because this thing is being way more discriminative in the sound that it accepts. You'll notice that the primary peaks still show up. And depending on what kind of analysis you're doing, it could be more preferable to have this sort of setup. Let's see what happens if we go the other way. Because as you all know, I like to go to extremes, right? let's live dangerously. I don't really think that's particularly dangerous, but we'll call it dangerous because it makes me feel better. And we'll go and we'll get some more pulse shaping. And remember, ignore this when you're doing the pulse shape. It always looks a little weird when you're doing the pulse shape. And we have this set now to 9, so we've gone from the bottom to the top. You can actually make it less than 1. You can make it 0.00001 and so on, but whatever. This will be good enough. Stop data acquisition. Accept the new values. And now let's run it. What's it look like when we accept every piece of garbage? We don't care. We don't care what it is. It could be sound. I mean, it could be electrical pulses coming in from my iPhone sitting next to it that's generating this. It could be all kinds of stuff. It doesn't look too bad, actually. This is a pretty good detector, and the pulses coming in are pretty well done. But you notice everything's a little bit jitterier looking than it was before. Give it time, it'll smooth out. But pretty much I find that 0.5 is the best setting for me. It provides the best looking spectra. Look at that. Not bad at all, though. Not bad. So let's get back to 0.5. 0.5. And let's do a calibration. How to do a calibration? Well, let's get back to 0.5 again, remember. Start shape acquisition. Let's get some shape, and then we get some pulse shapes analyzed. And then we're going to save those, and we're going to do a calibration. This is where the benefit of having the known radioactive isotope comes from, because without this, you're going to be out of luck. If anybody remembers my video where I went to the hotel room that was radioactive, I had to bring calibration sources with me to the hotel room because the temperature of the hotel room and other things could have affected my detector, and I might think that I know what type of isotope is in the room, but I could be wrong, and I want to be really accurate. The same sort of thing applies with this detector or any other detector like it. By the way, with my Polymaster, you might notice I don't have to do that with, and that's because it automatically adjusts for temperature settings and things from a known good calibration. But most units don't do that. So let's accept the pulses in their new settings and start data acquisition. And we're going to calibrate this sucker. All right. Here we go. Now we'll give this a couple minutes to calibrate, and I'll be right back. All right, so we have a beautiful cesium-137 spectrum. We're going to calibrate. Before we calibrate, let's go to data acquisition and analysis and quickly look at the logarithmic view and the bin size just to show you. Logarithmic view, click OK. As you can see, when in a logarithmic view, you're seeing a steadily increasing count size. So from here to here is maybe 1 to 10 counts. From here to here is maybe 100 to 1,000. From here to here is up to maybe 5,000 or 10,000, so on. So it's a curvature going up, a logarithm. And basically put, this can be very useful for looking at really low really low intensity peaks that could be drowned out by high intensity peaks. But it has a downside of sometimes producing some very odd shaped spectra that can be sort of hard to look at. I don't know how to describe it exactly. I find the logarithmic view to be usually pretty difficult to work with, but it can be useful in some respects. For example, if you were looking at a europium-152 spectrum. All right, let's switch back to linear. Linear, by the way, is a straight 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to whatever the max is. It's a straight linear progression. So we'll get rid of that. The other thing to show you is the bin size. That's like the number of channels. Many spectrometers have channels and not bins, but let's show you how that works. You notice that we're looking at 1 to 140. Well, 0 to 140. For example, right here is 310. And you notice that the number I put in here is 0.1. So that means that the actual channel I'm looking at right here is 31.2. So if I were going to calibrate, I would say that channel 31.2 is equal to 662 kiloelectron volts. Well, how do we change that? Well, let's make this 0.5. Watch what happens. All of a sudden, where there are a lot less channels. See? Look at that. We only go up to 140. One channel, two channel, three channel, four channel, five channel. See what I mean? Terrible. And that can be useful sometimes too, by the way, don't get me wrong. And we can go down to 0.1 again, and you get a whole bunch. So you can change the channels around if you want to. I would recommend not setting the number really, 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 really low, like 0.01 or 0.001, because the computer, the program itself can actually freeze up if you do too many. If you try to give it like 20,000 channels. Besides, it's not really very practical or useful. So keep that in mind. This number is 0.1, so we're going to multiply whatever we see here by 0.1 when we do our calibration. So let's go to Settings and Energy Calibration. There it is. Behold the calibration. As you see, 2 points are already calibrated for us. 32 kiloelectron volts and 662. It's actually 661.66, but most people just go with 662. It's pretty close. And these are for cesium-137, and they seem to come with the program by default. Anyway, there's several calibration modes to pick from. Fit slope, fit linear, interpolate. We're going to stick with fit linear for our basic usage of the software. The energy units we're going to go in are kiloelectron volts. You could go in like millions of electron volts, MeVs and so on, or even electron volts, but it will be impractical pretty quickly. keV is the right unit to use. And this is an arbitrary. You could write pickles if you wanted to. It wouldn't make a difference. It's just, this would say that it was at 662 pickles, which would mean nothing. So put a valid unit in. And what you're going to do is you're going to write the mean. This is the centroid of the peak. This is kind of like the center part, the highest part. It's not actually the highest. It's statistically the mean of the peak. You're going to put in the standard deviation, the standard deviations of the peak. I believe it's the first standard deviation it's looking for. I usually leave this as 1 because I'm not actually attempting to do my calibrations per se with this unit. I pretty much can pick out most of these by eyesight, but you can calculate the standard deviations for this. I'll go into that in more detail when I go into a video about how to detect isotopes and everything like that. This video is just sort of the basics of showing you how to use the software. So you can set that as 1 to start with, or you can set it correctly when you know the actual standard deviations for those particular energies. And last but not least, you need to know the energy you're looking at. We're looking at 2 energies. 32 kiloelectron volts, which is probably right here. bin 18, which is 1.8. 1.8, remember, multiply by 0.1, the arbitrary bin size. And now 662, which is probably right there. And that's 311. So that's 311. Put a point in there. So 31.1. Click apply. Close. I didn't do the other side because I only have one. Here, let me show you. I only have 1 channel of audio. You could have multiple channels of audio, right and left. I only have a left channel, so I don't really care what the right channel is set to. Okay. Now we're going to use energy calibration. Check the checkbox and click OK. And now we are calibrated. And as you can see, we expect that this will be 32 kiloelectron volts about. It's 34. Let's move over by 1. There we go. 32. And we expect that this will be 661.66, or actually 662 if you like. And there it is, 662. See, energy. This should be around 400 to 480, this Compton edge, depending where I click. 430, 420, that's pretty close. This backscatter peak should be right around 220-ish. That's pretty close. We could do a lot better job of calibrating this, by the way, too, and I'll go into that in a video where I go more in depth about isotope detection, where you need to get really, really good with your calibrations. But I'm showing you sort of the basics right this moment. And this peak right here comes from the actual lead shielding around the detector, and it should be somewhere around 75 to 80 kiloelectron volts. And that's exactly where it is. All right, so we are effectively calibrated. I mean, we could be better calibrated than we are, but I mean, this is a basic calibration. We know the detector's pretty much working. So let's take that soil now put it in the detector, run it for a short time, see what's in it. That'll be fun, won't it? We're going to stop the detector. And let's go prepare the sample. Okay, now we can take this filter and put it in front. And we could put a rock specimen in front. We could take this bag of soil and put it in front. And I think that's what we're going to do. We could also take a beaker like this, fill it with the soil. Beakers are a good idea because they block a lot of the beta if they're made of boron silicate like this guy. And we're going to sit back here and do an analysis and see what we get. Okay, with the sample now placed in front of the detector, we're ready to go again. Action, start accumulation. Now this doesn't have a big strong piece of cesium-137 in it, so it's likely that it will take a while for a spectrum to form. Now I'm going to speed this up for you, so what would be probably 10 minutes of spectrum accumulation is going to speed up to maybe a few seconds. So right now you see it at real time. This is what it looks like in real time. I'm going to speed it up now, and I'll be back in about 10 minutes time for you to see what the result looks like. All right. Well, the calibration is not absolutely perfect here. Excuse me, let's stop the accumulation. But we have a pretty clean spectrum. There's not very much going on in this actual soil sample. The soil samples that were much hotter that came from the mine area, well, they were rockier. But anyhow, in this case, some of the peaks are actually pretty small and hard to pick up. So we're going to switch, ironically, to the logarithmic scale. And in the logarithmic scale, you can get a better view of a few things. Now, the calibration is not dead on because at around 1388 kiloelectron volts, that actually should be 1461 kiloelectron volts, which would be potassium. This is a peak for potassium in the soil. The soil has potassium. And over here, that should be closer to 6.9, 6.10. You notice the calibration is a little bit better as you go down lower towards where we originally calibrated. And I'll go into details of calibration in another video, which explains why, for example, if I go over this direction, the calibration drops off. But that right there is a bismuth 214 peak. And I can't really pick out the rest of these guys too much, but this is some uranium in here, not very much. It's not actually uranium, it's lead 214. But basically there's your basic spectrum. And you can pick out those two features from it, and they are the result of uranium in the soil sample. Let's go into another feature here called show Gaussian correlation. And what this does is it's a little algorithm that will attempt to try to pick out real peaks for us. We'll see if it picks them out okay. Okay, now do you see the red? It found a peak right, see the red shape right there? It found that one right there, and that's potassium. Where's that one? And then where's this one? These guys are probably like protactinium or something like that, most likely out of this range. That right there is bismuth. It found the bismuth peak. That's from the lead shielding at 75, almost right on the dot. And some lower X-ray energy down here. So basically put, it looks like it picked out everything okay. It missed the lead 214 peaks, but they're probably not being generated very fast. So as you can see, with just a little bit of lead shielding, we were able to pick out something. We could determine that this soil sample contains uranium. If we had a lot more lead shielding, specifically lead shielding around the actual soil sample, we'd probably get a much cleaner view. But let's switch to a piece of actual uranium. So first off, let me go get the uranium, and then let's test it. All right, so we're going to replace the soil sample. And what we're going to do is we're going to take this beautiful piece of metatorbonite and put this right in front of it. Metatorbonite will do a pretty good job of lighting up the detector. Okay, so I've cleaned everything out, and I have logarithmic view cut off because logarithmic view is only really good when you're dealing with really low peaks that are being drowned out by other peaks. So the uranium piece is right up against the detector. Well, it's not right up against. It's about an inch away. What is that? 2.5 centimeters. Let's start data acquisition and see what we get. Now the uranium sample is a lot more potent than the soil sample, and so it's not going to take us very long to get a pretty clean spectrum out of this. And as you can see right off the bat here, the calibration is a little off. And remember, I told you in a later video I'll go into more depth of how to get that exactly right. But almost right on the dot here, you have bismuth 214 at 609 keV. You have lead 214 at right around 650-ish, or sorry, 350-ish, plus or minus. Let's see, should be around 295 or so. Pretty close. You have another lead 214. Here's another lead 214. Should be at, where is that? 148-ish. Pretty close. And radium 226. And some of these guys down here are from uranium 235 and so on. Yeah, that's pretty much a uranium spectrum. And if we were to give this a little bit more time, it would actually increase and become even stronger. We might actually want to lower the height threshold in arbitrary units. We might want to actually drop the height threshold down just a little bit for a spectrum like this, because these gammas, a lot of them are going to be coming in at the same time and bumping into one another. Well, they don't actually hit each other, but what happens is they produce photons at the same time. You get all kinds of little sun peaks and everything like that. And changing this number to a lower number, meaning that we need to keep everything much more uniform, is probably going to result in a better shape overall, a better spectrum. But as you can see, it's coming out pretty well. These are the three fingers of lead 214 and the thumb from bismuth 214 and of course radium 226. Straight up. Now let me show you the last and most important and amazing thing that PRA software can do for you. And again, this is made possible by the Gamma Spectacular, although you can do this without the Gamma Spectacular, but realistically speaking, unless you really like soldering irons, I would just go with the Gamma Spectacular. We can hit the space bar and we can actually listen. Let's cut the volume up. We can listen to the spectrum. What you are hearing is the sound of the photons. High energy photons are high peaks, high sounds, high tone sounds. Low energy are low tone sounds. That is uranium. And to prove what the difference is, let me add some cesium-137 and see if it changes. Here's cesium-137 added. Notice the difference? Let's get rid of the uranium and leave only the cesium behind. Amazing. And so that is the basic unit and the basic usage of the unit. And like I said, later on I will go into more detail about how to configure it and how to detect isotopes with it. I plan to make even more videos about it, but we're getting there. So this has been Tom from anti-proton.com, and I'm enjoying my B Research Gamma Spectacular.